All right, hello everyone. I'm here to talk about PicoTCP and how this can help in the tinification of the Linux kernel. And for that, I'll first give you some more context. Because we're all here to talk about the Internet of Things and about using small embedded devices to communicate with each other, to communicate with the cloud and things like that. And we've got this great operating system, which is Linux, and we'd like to use it as much as possible in the IoT. So this is briefly the content that I'm gonna go through, and the first point is the problem. What is the problem that we see for using the Linux kernel in the IoT? What can you do about it? What did we do about it, and how did we do it? So there's this famous quote that says that Linux runs on everything from cell phones to supercomputers, and while that's absolutely true, a cell phone nowadays, I took here the example of the Nexus 5, is a cell phone with 2.3 gigahertz CPU. It's a quad core, and it has 2 gigabytes of RAM. This is not what I think of when I'm thinking of an embedded device, and certainly not the device that we want to use in the IoT and small sensor nodes and things like that. So indeed, Linux runs on these systems, but this is a figure I stole from another presentation talking about the tinification of the Linux kernel. And at the bottom, I'm not sure you can see it, but here in the corner, there's kernel version 3.0 going to 3.17 at the right-hand side of the graph. And here we can see the minimum kernel size. Well, actually, it's not really the minimum kernel size. This is with make all no config, so it's a default kernel configuration. And what we see is that it's steadily growing. So your kernel is getting bigger and bigger with every version you get. There's a small bump there when the option was introduced to compile out the TTY, but other than that, it's always increasing. And this is not a good thing for tiny embedded systems. So what is a tiny embedded system? What kind of system am I thinking about here? For the example, I took a development board from Mcraft, and this has a Cortex M4 microcontroller on it, one from ST32F4. This is a microcontroller that's being used a lot on tiny embedded systems because, well, it's cheap, it's small, and has a lot of peripherals on board. It runs at 180 megahertz. And additionally to this microcontroller, on this board they added some SD-RAM, 32 megabytes, which is ample. You could do with a lot less. And 16 megabytes of flash, but this is just to get comfortable with Linux, and also as a development platform, it's nice to have a little overhead, but you can actually go a lot smaller on this system. And the Cortex M4 is a microcontroller that you would usually run bare metal or with a small real-time operating system on it. Here we're going to run Linux kernel on it. And what can you do to run Linux comfortably on this kind of boards? First of all, you'll have to use UC Linux because this CPU, which I just mentioned, has no memory management unit. So that's the first step you'll have to take. UC Linux has other interesting additional features to run in an efficient way on small embedded systems. But it's also only kernel 2.6, at least the version we used right now. So it's lagging a bit behind, but okay. You can do things like execute in place. So usually your kernel gets loaded and decompressed in your memory and RAM. You don't want to do that here because you can read the read-only data and the code straight from flash to spare some RAM. That's one of the things you can do. Read-write will, of course, still be in RAM. But the trade-off here is that you cannot use kernel compression anymore because you have to execute code in place. Another option that was added lately, I think somewhere 3.17 in the kernel, is make tiny config, because there is this movement of making the Linux kernel smaller, and this actually introduces some options like using the -OS switch from GCC to actually get that kernel size down. It's not in favor of performance, of course, but when you need the space, you need the space. But then we thought about something else. What if we could replace the TCP/IP stack? I mean, Linux kernel runs on so many server computers all around the world, but we're trying to reach the other end of microcontrollers here, not the big servers with tens of CPUs and gigabytes of memory. We really want to go to the small side, and the TCP/IP stack in the Linux kernel is not focused or built for these kind of devices. So that's where we come in. We've got this project that's called PicoTCP. It's a free software project that's backed by the company I work for, and we wanna promote this stack as the reference TCP/IP stack for the Internet of Things. It's a stack that's fully featured. There's really a lot of features in there, but it's also very modular, so you can really select every single thing that you want or don't want in. And it's highly portable. It runs on anything from an 8-bit AVR up to a 64-bit server computer. You can run it inside an operating system or just bare metal. And now you can also run it inside the Linux kernel instead of the TCP/IP stack that's by default in the Linux kernel. So that's where I'm going to switch to a little demo, and the setup is very simple. It's not going to be anything spectacular, but it's just to show you that it works. It's this board with the Cortex M4 on it, and my laptop connected by an Ethernet cable. And first thing I'm going to do is reboot the machine and go into the bootloader. And from the bootloader, I'm going to run a netboot command, which is going to boot the kernel with the TCP/IP stack in it from TFTP. And there it goes. It's starting, and as you can see, it's also booting pretty quickly. So the kernel's booted now, and the last line here is already an output from PicoTCP, which has assigned a loopback interface. Now I'm going to configure ETH0 to have an IP address and a net mask, like this. So okay, this again is a print K from PicoTCP saying that it has indeed assigned this IP. So let me now try to ping the device from my machine, and we see indeed that it works. Okay, great. How can I now be sure that it's PicoTCP? I'm not just booting some random Linux kernel. We added some interface for that to the kernel as well. And it's just a small variable that you can cat, and indeed, okay, procnet stack is now PicoTCP instead of the standard TCP/IP stack. And a last thing I want to show in a demo is I'm gonna wget a binary from my computer. This is iPerf, which you can use to monitor network performance. I'm going to start an iPerf server on my laptop here. I'm going to connect from the board. So it should try to connect. And this is also where you see that we still got some work to do. We got an average throughput around 1 megabyte, sometimes a bit more, sometimes a bit less. And this is just a proof of concept for now. And this is a tool that we use to check if the performance is up to if it's up to speed or not. So okay, we saw the kernel running PicoTCP, and now I'm going to explain why we did this and how we did this. So what we did is first remove the TCP/IP part of the kernel, just to know how big is this. Well, if you remove all of the networking, you remove about 400 kilobytes of the kernel size, but we kept the whole networking infrastructure because you need sockets on the local host to do some things as well, and also we reused the devices interface from the Linux kernel. But we have removed the TCP/IP part, so IPv4, and that saves about 160 kilobytes, and that's 10% of the kernel size that's running right here. Then we added PicoTCP instead, also IPv4 only, and this added 40 kilobytes. So that's where we see that PicoTCP is made for the embedded systems. It's only 40 kilobytes. And this means that for the same functionality, we reduced the kernel by more than 100 kilobytes. How did we do this? So first part is very easy. In the kernel .config, you set inet to no, but you still need net equals yes. So net is the part that I was talking about that's providing you the device's interface to transmit packets. Then we added a new module, PicoTCP, and you can enable it by setting PicoTCP equals yes in your .config. And we added the complete PicoTCP source tree, as you can find PicoTCP on GitHub, and we added that to net/tcp/ip/PicoTCP. And then we created a kconfig so that we can enable this. We created a makefile to select the right sources. We modified the original kconfig, and then we needed some glue logic because we got the PicoTCP in one corner, and we got the normal Linux kernel with its interfaces that it was used to use, and we need some glue in between of that. So the glue logic adds this. We implement these proc files, which I showed you procnet stack before. Okay, you don't really need procnet stack, but there's a few other proc interfaces that you do need. Also in procsys. And then IOCTLs. So IOCTLs is one of the ways you can communicate with the kernel from user space, and there's a lot of socket IOCTLs actually in the kernel. For example, to set your Ethernet address, as I just did with iconfig. So you need a bunch of IOCTLs, which we also added to this glue logic, and these IOCTLs are then going to be translated to the native PicoTCP API, so that it understands what the kernel was trying to do or what any tool from user space was trying to do. Then we need to register the inet protocol family, and especially these IPv4 protocols again, because we just removed them by commenting out inet. And then another step that we need to take is to modify net device, which is this layer that allows you to communicate, receive and transmit packets to any network device that the kernel supports. And we have to reroute these packets to and from the PicoTCP stack as well. So we did all of this in basically 5 files. The 6th is still a stop for now, and I'm not going to show you actual code, but I'm going to go through these 5 files and explain you what part of this glue logic it implemented. And you can find all of these files, by the way, in linux/net/tcp/ip, which is a new folder that didn't exist before. So core is the entry point. It has the __ init, and this will call pico stack init, which is the initialization routine for our stack, and also af inet tcp/ip init, which is in another module, which is going to register this address family. And it's also going to schedule pico stack tick, and this is the clock that our stack needs to be called every once in a while. And we do that using a work queue in the kernel. Next file is af inet, so that's for address family inet, and this is gonna register actually this protocol family again, which we have stripped before, using there's structs in the kernel like proto-ops, and there you can set all kinds of fields to the callbacks that the kernel is expecting there. And in this file, we also implement all of the BSD socket calls that you would normally use on sockets, like accept, bind, connect, and so on. So they are not actually implemented in this file, but they are calling the original PicoTCP API from there, but using the API that the kernel would expect from these functions. Next file is netdev. This is the link between the stack and the kernel's network device abstraction. And this is actually really nice because we can reuse any Ethernet or other network device driver that already exists in the kernel. We don't have to rewrite everything from scratch because we just changed TCP/IP stacks. And this is where the link happens. So packet send, packet transmit, and also the attach function. When you're gonna up or down a device, that's also where the link is happening. And then we have IOCTL. So that's the IOCTLs to call kernel functions from user space. Tools such as ifconfig are going to use these. And here's a few examples of IOCTLs that are implemented. That's get address, get MTU, set flags, things like this. Last file is proc.c, and this will implement a procnet route. And you guessed it, you will need to use the route utility. So procnet route is gonna set or gonna give you a list of all the routes that are configured right now. So PicoTCP, although it is a very small embedded stack, has IP filtering and routing and things like this set up. So you can still use all of these features. And it also implements the procnet stack, which I catted before, that just prints PicoTCP. The last one is net.c, so that's not really there right now. It's just a stub, but we implemented this because RT netlink is a new, well, relatively new configuration socket, and that's used, for example, by IP route 2. So if you're going to try IP route 2 on this proof of concept, it's not going to work yet. But all the stubs are there for the callbacks that are needed, and if someone wants to give us a hand, they can implement these, and we get more functionality. So, to conclude, we have more or less the same level of functionality. Of course, it's just a proof of concept. Not everything is there yet, but it's perfectly possible, especially when you focus on the embedded devices. I'm not going to say that you can use PicoTCP and run your web server on top of this, or at least not in a big server farm, at least for now. But for an embedded system, I don't think you will miss any functionality because PicoTCP is really very complete. You get a smaller and a faster kernel. You get less RAM usage because PicoTCP is tailored for these embedded systems, and you get less ROM usage as well because the size of the kernel is at least 120 kilobytes less. And the boot time I measured here is about 15% faster. It was already pretty fast, but now it takes 1.04 seconds instead of 1.23, which is also nice. And you get less RAM usage, as I said before, but here's one of the figures. I counted proc mem info. You get 216 kilobytes of actual RAM that you can use more. Okay, on this system we had 32 megabytes, but if you're using a board that only has 4 megabytes, then this is really, really important. But of course, there's still a lot of things to improve. This is just a proof of concept, as I said before. Throughput is average. The same board with the original Linux kernel goes somewhere between 5 and 10 megabits per second. PicoTCP certainly can handle these speeds. We have embedded systems running bare metal that do Ethernet line speeds, 100 megabits. So it's a problem with scheduling inside the kernel for now. The RT netlink API is not completely yet, as I stated before. Raw sockets also are not supported. And what do you need raw sockets for? For example, the ping command is going to use raw sockets. So for now, the board will reply to pings, but you cannot send pings to other targets because that will require raw sockets, and we don't have them. And this is actually because PicoTCP has no raw sockets for now. On the other hand, there is no IPv6 support yet, and that's not because of PicoTCP, because PicoTCP supports IPv6 very well, but it's just the lack of glue logic and more interfaces to make there. And that's it. Here I put a bunch of links. Myself, I am Maxime Vessard. I am a low-level embedded systems engineer. The company I work for is Altron Intelligent Systems, which is also backing the development of the PicoTCP project. It's a free software. It's an open source project. It's on GitHub. The kernel I just demonstrated here is also on GitHub. Here's the link. And PicoTCP itself has a website, picotcp.com. You can find it on GitHub as well, and you can mail us. You can send some pull requests for this kernel we just demonstrated, or just try it for yourself. And that's it for me. So if there's any questions about this, I'll be glad to answer them. Yeah. So how safe is it to expose this stack to the real internet? We are doing quite some testing on our stack as part of the project, and we're aiming really hard to comply to all the RFCs we implement. So it should be pretty safe. I'm not saying that there is no possibility to find some nasty buffer overflow or to crash the board. That is a point for sure. But the stack is being used in a lot of embedded systems that are connected to the internet, just not through the Linux kernel for now. So we're testing pretty hard on that. Yes? We haven't focused. So the question is this just a quick hack, or is it easy to plug another stack in the Linux kernel? Is that right? Well, I must say we haven't focused on making the kernel interface to network stacks very generic, because that's not something you want to do often. And especially for us, the focus was getting PicoTCP in the kernel, and not opening up or making the kernel interface as clean as possible to plug any stack. So, not really, no. Yeah?
You said that you are testing it quite hard.
Yeah.
Does it mean that it is already stable?
PicoTCP is already stable, absolutely. We're very proud of that, and you can even check our test results on GitHub. We got a link there. But the port to the kernel here, which I demonstrated, is absolutely not very stable, no. It's a proof of concept, absolutely, for now. But we plan on developing this further, especially because there is some interest on the Linux kernel mailing lists and things like this for getting the kernel size down to use it on Cortex M3 or even smaller systems, which is not possible with plain Linux. Yeah?
Certain people, especially in the HPC world, are crazy about latencies and like. They actually run, well, I have no idea what the source code is, but they run PHP stack in user space.
Yeah.
Have you tried similar approach? It could actually save even more space.
So the question is, there has been some projects where TCP/IP stacks run in user space to get better latency and things like this. We did this with PicoTCP also. We actually started off as running this in user space first, because it's easier to do. But there we're still using a TUN device or a tap device to get it out to the actual network stack. We haven't specifically done any latency comparison in that field, but it was very good. From what I remember, we get a lot of throughput and really good latency running the complete stack in user space. Yeah.
Have you saved any extra space? Did you do the space saving comparison?
No, because at that point we still kept the whole networking infrastructure that was in the kernel. I'm not sure how easy it is to have a TUN or a tap device and throw out all the rest. So that's an exercise we didn't do. But it's perfectly possible to run PicoTCP in user space. Yes. Yeah, in the back.
If I just need Linux box that just sending me packets like temperature, just pushing a value once in a while, how low can I compile to TCP? Because you said it's 43 kilobytes.
Yes.
But it's with the TCP/IP. If I just need UDP,
Yeah.
how small can it be?
Well, I haven't tried only UDP in the Linux kernel, but PicoTCP with just UDP support should go somewhere near 20 kilobytes. I can maybe show you a compilation of PicoTCP right here. Okay, sizes are not great. Okay, TCP is still on. Let me disable TCP and see how big it ends up. And enable UDP. So there, okay, it's 50 kilobytes. That's weird. I probably missed some optimization. Yeah, it should be somewhere around this. Yeah, I got 24 kilobytes right here. Yeah. Yes. Yeah. Yeah. Other questions? All right, thanks a lot.
Thank you, Maxime.
Yeah, thank you.